eradicated, and they've spent 250 million on it, but they're still trying. And this project was to try and help them decide if they should keep throwing money at it. And we just built a model. We predicted how long it's going to take to eradicate it, how much it's going to cost, and what it's going to be worth to people in Queensland and Australia. We came up with some conclusions, and I'll run you through some of those in a moment. But before I do that, I just wanted to do something. I just feel this need to give some general take-home messages instead of saying, hey, we looked at a case study and we found this and we told the client that and they're happy. You know, I could just do that, but I'd rather say, hey, we did this project just for fire ants. But it turns out that some of the things we found out can be applied to lots of other invasions. And there's a little bit of economics in it as well. So I get to present it at an Aares lunchtime meeting. So I felt, how do I get economics into this? It didn't start off having much economics, and so I want to emphasise the economics part of it. So economists love discounting and graphs and stuff. So I've got some pictures with graphs. I'm going to talk about discounting. This first graph I put together after talking with Anne Cole, actually, who's sitting in the front. We've been looking at this curve a lot, haven't we? And it shows you different types of invasive species control programs. The best ones are the ones where you stop them getting into the country at all, and by the time they've come into the country and they've spread, and they're everywhere, the only option left to you is to just get rid of them on your property, pretty much. Pull weeds out from your garden. When you're pulling weeds out from your garden, you pretty well know the cost of doing it, so you know how much your time you're putting into it, and you also know the benefits of getting rid of it. And they both happen roughly at the same time. A lot of the costs and the benefits happen at the same time. When you move further to the left on this diagram, you get costs incurred up front, and the benefits start happening later and later relative to the costs. And you know less and less. Because the benefits haven't happened yet, most of them don't happen for years, and because a lot of the benefits affect, I don't know, ecosystems or lifestyles. People can't go out and have barbecues with bare feet anymore if there's stinging insects. They have to wear shoes. We don't know what that's worth. We don't know how much it's worth to people not to be able to walk out in their garden with their bare feet. And as a result, we don't really know the benefits of eradication programs as well as we know the costs. So the first slide just emphasises that. The other thing we don't know, and we'll probably never know, is how fast an invasion spread. It's all very well to say we don't know what it's worth to you to have your bare feet in your garden. But I don't know when you're going to get fire ants in your garden. I just don't know when it's going to happen, because I actually can't predict how fast they're going to get to you, almost in any single case. And the reason is you can infer how fast something spreads based on data. You can say, look, I've looked at this invasion over 10 years. In year 1, there was 1 hectare with fire ants. In year 2, there was 2 hectares. In year 3, there was 5 hectares, and I can plot all of those points on a graph and run some regression. And I can say, well, it's spreading at 5 hectares a year. Now, if it takes 5 hectares a year, well, that works out to be about 10 years before it gets to your garden. The issue is that that 5 hectares a year really can't be observed directly at all, because as soon as fire ants were discovered in Queensland, they started killing them. We don't know how fast they would have spread if they weren't being killed every year. If they weren't being killed every year, there would have been a lot more of them, and they would have found it a lot easier to breed and spread, and they would have spread a lot faster. But we didn't observe it. And so we're really kind of guessing how long it's going to take before it gets to your garden. So that's a really statistical problem with working out benefits and costs. You can't infer spread rates from data. Not that easily. Discounting, and I put this slide in solely because economists do discounting, because when I looked at this project, there is not a lot of economics in it. Discounting changed the results of our model completely. We ran the model for 2 discount rates because the Department of Finance in Canberra, or Treasury, insists that government projects get evaluated with a 7% discount rate. This was in April or March this year. I don't know if it's still the case. I originally ran it at a 3% discount rate, and I didn't have any good reason for that either, but it was just agreed at a meeting to do that. In any case, the results are completely different. When you change the discount rate to 7%, you should spend a lot more money on fire ants. Sorry, you should spend a lot less money on fire ants. So I want to explain why that happened. Benefits and costs happen roughly the same time at the end of the curve, and they happen at different times at the start of this curve. Invasion starts at the left and moves its way towards the right. At the start, if you prevent entry or if you eradicate them, you incur a cost now, and the benefits happen a lot later. So if you increase the discount rate, those benefits are less important. So we'll talk about what that means later, but the effective increase in the discount rate is to push your best strategy towards the right, at least for some of that range. Here's a picture of an invasion. There's an area that people have thrown pesticide and have gone searching for them, and that's the grey area. And then there's the true edge of the invasion, which we don't know, we can't observe, but I've just drawn it as if we do know it. So that's just a way of depicting it, and then I'll show you what you can do with this picture in the next slide. So, if you have an invasion that you think's gone way to the edge of the city, started in the elephant and wheelbarrow, somebody came in here, got off the boat, didn't know they were carrying a couple of beetles, they were reproductive, they crawled down to the bottom of the street, started reproducing, and they're flown to the botanical gardens. One way that we could get rid of that invasion is to go to the elephant, to wait for the first person who is eating lunch here, getting stung, telling us, hey, what's this weird thing, ringing up an entomologist, saying, is this new, going through a whole lot of steps, and eventually saying, oh, it's terrible. Ring up Canberra, get an emergency response in place, get approval to get funding for it. That takes a lot of meetings, a lot of cajoling, get a lot of money for it, and then start doing stuff. The first thing that will come to your mind is what strategy we're going to use to get rid of these beetles. And one of them is an inside-out strategy, and that is, okay guys, let's get 50 people starting at the elephant wheelbarrow and let's walk in 360-degree directions around here, as far out as our money, as the budget goes. That's called an inside-out strategy. Another one would be, let's just start out over in Brunswick and all the way down to the bay and move in. And that's an outside in. They've done an inside out strategy in Queensland up till now. They tell me that they're switching to an outside in just now this year for the first time. But I'm going to look at an inside out strategy. Now an inside out strategy works if the area that you search each year and spray grows faster than the edge of the invasion, because that means eventually you'll catch up with the edge and you'll win. So, if somebody's telling you, should we spend $250 million to get rid of fire ants, and you have to give them some confidence that you're going to win, you have to do a few things. You have to infer how fast that edge is growing every year, and you have to predict how fast the grey area is going to get to the edge. And that's not easy. So one of the questions that I looked at was, is it better to spend a lot of money each year or less? People in Queensland would love to spend more money each year and convince Canberra to spend more money each year. Then they get a lot more people trying to kill fire ants, and it's a bigger program, and that grey area would then be bigger each year. You'd basically grow faster. If you double your budget from 10 million, they're currently spending roughly, this year they've got 18 million, of which say 4 or 5 million is on head office staff and logistics, and that leaves you with 10 or 12 or 13 million to go out and spray them and find them. If you're spending, but in the past it was closer to 10 million a year, I think, just recently. If you're spending 10 million a year, you can find the fire ants, we estimate, in about 11 or 12 years probably. If you're spending 20 million a year, you can get them in 4 or 5 years. Which is better? Is it better to have this huge budget or a smaller budget? If you use a huge budget, you're spending more this year, much quicker will we get to the edge of the invasion? This is where discounting is going to come into this in a moment. So if the advantages of spending more each year, there's fewer people are going to get stung by fire ants, and you're going to find the edge of the invasion quicker, so you'll get rid of it quicker, sooner. Is it good to get rid of an invasion sooner? Well, I think in general, the number of people who are avoiding getting stung is going to be tiny. Get rid of it sooner, 5 years sooner. How many extra people are going to be prevented from getting stung? Not many. Why? Why is that? Because most invasions thin out towards the edge. It started at the elephant and wheelbarrow, and it wasn't detected for 5 years, and by the time 5 years came, there were millions of them here, but there weren't that many of them near the botanical gardens. An inside-out strategy starts at the elephant and wheelbarrow and goes out. So if I spend half as much money each year, it just means that it'll take longer for me to get to the botanical gardens. But so what? Because there was only about 5 nests there anyway. Hardly anybody got stung, so really what are we saving? Not much. So you would only spend a lot of money to get rid of an invasion if not spending a lot of money causes the invasion to spread much faster, and if there's some really important stuff near the invasion edge, like some important ecosystem that's going to be lost if you don't stop the invasion getting to it. But if it's just people you're worried about, you wouldn't bother with spending a lot of money because there's not that many ants near the edge. And it's the edge that you find last. So the fast strategy is above the line. Year 1 you do a little bit, and you gradually by year 4 you've gotten rid of all of them. That's the whole grey area. And slow, it takes you 5 years instead of 4. And by the time you get to the 5th year, the invasion's bigger because you've had an extra year or two, an extra year for it to spread. So which of those two strategies is better? Well, we found as soon as you change the discount rate from 3 or 4% to 7%, you switch from fast eradication to slow. And that worried me because the idea of letting these things stick around for another 6 or 7 years worried me. Just because somebody changed one number in a model, the discount rate, all of a sudden we're letting people deal with fire ants for another 6 years. Does that sound right? So people don't like fire ants. This is a person who volunteered to put their arm in a nest of fire ants. It was just like, he did it for fun. His arm looked really ugly. Big part of Australia could support fire ants, so people would be worried about that. Basically, people would be worried. And so they're willing to pay some money not to have fire ants. And Tom Kompas and Sonia Actor estimated how much they'd be willing to pay not to have fire ants biting them. This is a difficult and interesting project because they've spent more than 250 million. And there's no sign of eradicating it. And people are wondering, how come we've spent so much money? They use surveillance and they use chemical treatment over big areas. That's where the money's gone. So it's a difficult decision because there's large benefits of not getting stung and making people feel comfortable, but there's big costs, and we don't know if we're going to eradicate them anyway. So, in the past, they started off just by using treatment. So the red area on the top left of that diagram is the area that they actually applied chemical treatment. And it's almost the entire area. They didn't do any searching at all. They just bombed the place. They went to the port of Brisbane and they bombed it with poison. Not that many people live there, so you can get away with it. And then they started increasing the area because they started finding a few nests on the edge. So they increased the area that they poisoned, but they added a little bit of search. The search is yellow. You can see that as you go towards the right, there's bigger areas of yellow. And blue is both search and treatment. What it doesn't show is how many times they repeated the treatment. They actually did it 6 times. They put the same poison on the same place 6 times at the start. And so I just did a paper with somebody else that said if they did it 3 times and they'd used the money saved to go out further, they would have actually eradicated this thing. But because they wanted to bomb it 6 times, they use up most of their money on poison. But it sounds like it's obvious that they should have spent less on poison and more on search, but there's good reasons why you can't just go and throw treatment over huge areas, because people don't like having... Would you like it if somebody drove to your property and threw poison bait all over your garden? People don't like it. So it wasn't that easy to do that. Anyway, by the time we got to the current situation, we're searching bigger areas, but it's still small compared to the amount they spend on poison bait. So we just did a study, Jonathan Keith from Monash and myself, that showed that if in 2005 they probably would have almost won it if they just searched another few 10k further out, 10 or 15k further out. They would have got rid of it. And they didn't because of various logistical and political and other reasons. But also, it's not that, it's 2020 hindsight's a good thing. I don't want to say that they've made mistakes. With the knowledge they had back in 2004, they were doing a good job. So this is coming out in PNAS next week. If anyone wants to have a copy, I'll give you an advance copy. Signed copy. That's the game changer, was remote sensing. And I recommended that in 2007, and it took about, after lots of phone calls, lots of meetings, it took 2 or 3 years for them to actually think about buying a camera and putting it on a helicopter and flying it. I think it actually took them 4 years before they started doing it, because it's just difficult to get approvals, and I don't know. There were difficulties, but it was the only way to find fire ant nests over a big area. If you can fly over 200,000 hectares in a year, there's no way you could walk across 200,000 hectares with people. You'd need 100,000 people. So we did this study for Tom Kompas at the Australian Centre for Biosecurity and Environmental Economics at ANU, and then also for ABARES, because this was done as the cost-benefit study to decide, do we give up on fire ants? So we simulated it. We built a simulation model using the model developed there, which told us how fast they're spreading and how many fire ants get found by people. So let's talk about fire ants that get found. We underestimate. So these are the way we calculated benefits and costs. Costs are just the search and treatment costs. We ignored head office logistical costs. Benefits are people's willingness to pay to avoid having contact with ants. This willingness to pay we estimated for 2 probabilities of coming into contact with ants, low and high probability. So people are prepared to pay a bit more if they're right in the middle of a hotspot of fire ants. If they're in an area with few fire ants, they're not willing to spend as much. Much less, actually. We ignored benefits past 20 years, and we ignored benefits outside of southeast Queensland. So 95% of Australia we ignored. And benefits keep happening for the indefinite future, so we've ignored most of the benefits as well. But it turns out that most of the benefits happen within southeast Queensland within 20 years. Because discounting, by the time it gets to Melbourne, 30 years later, a 7% discount rate is not worth much. Still, the benefits are probably substantially higher than what we estimated. And therefore, you can only use the model we built to choose between eradication strategies and not to tell us what it's worth. So they're the strategies we modelled. A small budget, but close to the current budget of 10 million a year on search and treatment, or double it, or a bit more than double. We allowed them to sort of inject nests, because only if they found a nest, this is the sequence of events. They fly over it with a helicopter, they fly over Queensland with a helicopter, they take some photos. If they find any nests, they go to the ground, they actually drive to the site and they say, is that a nest? If it is a nest, they'll kill it with a nest injection. So, I'll just go to the strategy we used. We assume that it's just too expensive to search on the ground. So once you've confirmed that that's a nest, run this model that predicts a probability map of where they are. The area with highest probability gets treated with this poison that they fly over the area and just dump it over you. And on the edge of the treated area, do a quick search on the ground. No, actually, with a helicopter. So that's the cheapest way to get rid of fire ants that we could come up with. And our results were that benefits were almost identical no matter what you do. And I think that's a reasonably general result, because invasions are thicker at near the beginning of the invasion point than at the edges. So an inside-out strategy will always have very little benefit. So long as you treat a big area in the middle, you get rid of most of the nests, most of the invaders. There's a few stragglers on the edge. Getting rid of those stragglers quicker it's not worth much at all. 3 people in that suburb there will not get stung. That's 3 compared to the 3 million people who have been protected from fire ants by doing this. Having a small benefit to 3 people is worth next to nothing compared to the benefit to 3 million people. Costs were different between spending more. If you double your budget, your cost is a lot higher. It takes less time to get rid of the fire ants if you double your budget. So the total area that you spray is smaller, but all of those costs are front-loaded. They're happening now. Discounting makes those costs, high discount rate means that if I took longer to eradicate it, and I can just push all the problems into the future, and end up treating a much bigger area because it spreads, that strategy of delaying eradication actually comes up cheaper. So benefits are the same, but it's cheaper to delay, so let's delay it. And that was one of our findings. That was the main finding. The other finding was those helicopters don't detect at least 70% of the fire ants in the areas that they search. You won't eradicate, and they need to double their budget. So this is what went up to the meeting. Should we spend more money on fire ants? Our advice was 2 things. Our advice was, if you want to keep the current budget, it's very risky because we don't know how good remote sensing is. So you're spending 18 million without knowing if it's going to work. You should double it to 36 or 20, actually in our case it was 21 million. You should double it because it's safer and it's worth it. But that advice was not really accepted because they've gone with 18 million, of which probably a big part of it's going to logistics. So they're only going to spend 11, maybe 12 million on searching. And what we predicted is that won't be enough. Probably. And that's really where we're at.